Welcome back. As mentioned before, we so far looked only at graphs graphically. Now we want to store graphs in matrices because that makes it easier to transport them on a USB stick or send them from one researcher to another. Because if you always share the picture, well, that's difficult to do math with. So in order to store a graph in a matrix, we do this in an adjacency matrix, where we simplify the graph into a matrix form. And every node there represents one of the rows and is also representing one of the columns. So row 1 and column 1 are both representing node 1. And what we see then in that matrix in the element A11 would be the connection between node 1 and node 1, in that case a loop. And if you think of that and that every node has its own column and its own row, you also know that this matrix must be squared. And the elements on the diagonal are the loops, and everything else is a connection. And in undirected graphs, this adjacency matrix is also symmetric, because every connection from node 3 to node 4 is also a connection from node 4 to 3. In directed graphs, that's different. There, the direction has to be made clear into the adjacency matrix. And there, we use the row as the source from where the edge is coming from, and the column is the target where the connection is leading to. So if we look at this undirected graph that we've seen before here with 6 nodes and 7 edges, which is undirected, you also have the adjacency matrix here. So you see in element 1, 1 that the node 1 does, the node A does not have a loop, but you see that the node 1 and 2 are connected because that's where the 1 is given. So you have the way of having the graph visually, which is easy to understand, makes it simple to look at, and the adjacency matrix, which allows you to work with that later on. And also, once the graph gets a little bit huge, like let's say Facebook or another social media outlet, where you have millions of people joining and even more connections, you can't even look at the graph anymore. You want to simplify it in some way to transport it. And so the adjacency matrix makes it more visually. In directed graphs, here, the same ones as you've seen before, also the two differences, we have non-symmetry in the adjacency matrix. And you also see that the direction of a node, of a graph, of an edge, here we go, that's the correct word, has an impact on the adjacency matrix. On the left side, we have the connection from node 3 to 4 or to 5, highlighted through this 1 and the 0 highlighted in red, that the connection is going from node 3 to 5. On the right side, we flipped the direction from 5 to 3. So there you see not just that we lose the symmetry in directed graphs, but you also see that the direction is really, really important on how the adjacency matrix looks like. In weighted graphs, we can also have an adjacency matrix. So far, we only had simplicity of 1 if there is an edge and a 0 if there's no edge between two connections. But in multigraphs elements, the amounts of edges between two nodes can be represented in that matrix. So if you have 3 edges, for example, you would add a 3 instead of a 1. And in weighted graphs, you put the weight of the edge into the adjacency matrix, for example, 3.5, if this is the connection between two nodes. So if we look at this multigraph with loops, you see the loops are on the diagonal with the ones. You see the multi-edges in non-1 values. Here you have, for example, the 3 connections in the top left that are expressed in the element 1, 2, 3, 4, 5, 1, 5. So here this multigraph has way more information. In a weighted graph, for example, it could look like this. So the weight between node A to B in element 1, 2 here is 3.1. And you also see clearly that this is a directed graph, as it's not symmetrical. The connection between B to A in element 2, 1 is 0. So here we have the directed weighted graph as a representation, how we can store a matrix and graph in a matrix form, and therefore can do matrix multiplication and other operations and to further get insights into the matrix.